Welcome to a comprehensive review of diffraction, a fascinating wave phenomenon that reveals how particles spread after passing through obstacles or slits. Diffraction is not just a physical curiosity, it's a window into the very origins of our universe. Today we'll explore how this concept challenges conventional theories like the Big Bang and string theory, and introduces a unique perspective: the universe as a result of the diffraction of an immense divine flashlight. Let's embark on this journey to understand how waves, particles, and the very fabric of reality are interconnected through diffraction. Imagine the universe not as a product of a cosmic explosion or colliding strings, but as the outcome of God's immense flashlight passing through a special slit. This slit, unique in its character, can break even light into its constituents, creating celestial bodies like Earth. This perspective invites us to rethink the origins of everything we observe, suggesting that the universe's structure is a direct result of a grand act of diffraction. This imaginative approach sets the stage for a deeper dive into the physics of waves and particles. The heart of diffraction lies the dual nature of matter. Everything is both a wave and a particle. This duality is essential for understanding why diffraction occurs. If particles, which are fundamentally strings, were not quantized, diffraction would be impossible. The quantization of waves and particles allows for the transformation of one physical state into another, making interaction and the exchange of physical quantities possible. This concept is foundational for the rest of our exploration. Let's break down the relationships. Particles carry waves carry charge, charge carries energy, and energy carries mass. This chain means that when a wave diffracts, it can influence the charge and energy of a particle. Quantization isn't just for particles, it applies to waves and charges as well. The ability to transform between these states is what makes physical phenomena and interactions possible. Without quantization, the universe would lack the dynamic exchanges that define its behavior. Fraction is more than just a spreading of waves, it's a transformative process. When a wave passes through a slit, its characteristics can change, leading to new physical properties. For example, the charge of a particle can actually increase after diffraction. This is a surprising result, challenging the common assumption that properties like charge remain constant. The slit acts as a bridge, converting wave behavior into charge and charge into particle properties. Understand how diffraction transforms physical properties. We can draw an analogy to Archimedes' principle. Originally applied to fluids, the principle states that pressure exerted at one area equals pressure at another. Since both water and light are electromagnetic waves, we can extend this idea to light passing through a slit. The pressure exerted by particles at the slit is equal to the pressure after diffraction on the viewing screen, forming the basis for our calculation. Pressure is defined as force divided by area. At the slit, the force exerted by a particle is spread over the area of the slit. After diffraction, the force is spread over the area of the viewing screen where interference patterns appear. By equating the pressures before and after the slit, we can relate the forces and areas involved. This relationship is crucial for understanding how the properties of particles change during diffraction. Mathematically, the pressure at the slit, P1, equals the pressure at the viewing screen, P2. This leads to the equation F1A1 equals F2A2, where F1 and F2 are the forces at the slit and screen, and A1 and A2 are their respective areas. Rearranging gives us F2 equals A2/A1 F1. This equation forms the backbone for calculating how particle properties transform through diffraction. Force exerted by a moving particle is given by F equals \frac mu 0 E2 F22 \pi$, where E$ is the particle's charge, F$ is frequency, and \mu 0 is the permeability of free space. This formula allows us to calculate the force before and after diffraction, using the respective charges and areas. By substituting these values into our pressure equation, we can see how the charge changes as a result of diffraction. By substituting the force equations into our pressure relationship, we derive a formula that links the charge before and after diffraction. The result shows that the charge after diffraction, E2, depends on the ratio of the areas and other physical constants. This means that as the wave spreads out, the total charge observed on the viewing screen increases, a direct result of the diffraction process. Increase in charge after diffraction might seem counterintuitive, but it reflects the transformation of wave behavior into charge. As the wave passes through the slit and spreads out, its quantized nature allows for a greater total charge to be measured on the viewing screen. This concept is not only fascinating, but also has practical implications for fields like signal processing and quantum physics. Quantization is the key to understanding why the number of particles and the total charge can be calculated so precisely after diffraction. Each particle on the viewing screen is a quantized entity, meaning its properties are discrete and measurable. This allows us to use simple equations to determine the number of particles based on the total charge observed. Once we know the total charge on the viewing screen, calculating the number of particles is straightforward. The equation E2 equals Ne$ relates the total charge E2 to the number of particles N$ and the elementary charge E$. Rearranging gives N equals E2/E$, allowing us to determine the maximum number of particles present after diffraction. The elementary charge, denoted as E$, is a fundamental constant in physics. In this context, it's given as $1.08 times 10⁻18 coulombs. This value is essential for calculating the number of particles after diffraction and highlights the quantized nature of charge in the universe. Realization that diffraction increases particle charge has important implications for signal processing, especially in spacetime applications. By understanding how waves transform into charge, engineers and physicists can design better systems for communication and measurement. This connection between fundamental physics and technology demonstrates the practical value of theoretical insights. Diffraction isn't just a theoretical concept, it's observable in everyday life. From the patterns created by light passing through a small opening to the behavior of sound waves around obstacles, diffraction shapes our experience of the world. Recognizing these patterns helps us appreciate the underlying physics at play in common phenomena. Study of diffraction has a rich history, with contributions from scientists like Sir David Brewster and Archimedes. Their work laid the foundation for our modern understanding of optics and wave behavior. By building on these insights, today's theories continue to evolve, offering new ways to interpret the universe. Today, diffraction is central to technologies like X-ray imaging, quantum interference experiments, and wireless communications. These applications rely on our understanding of how waves and particles interact with obstacles and slits. The principles discussed here are not just theoretical, they drive innovation in medicine, engineering, and beyond. The idea that the universe originated from the diffraction of a divine flashlight challenges mainstream theories like the Big Bang and string theory. While speculative, this perspective encourages us to think creatively about the origins of the cosmos and the role of fundamental physical processes in shaping reality. To recap, diffraction is a powerful phenomenon that not only explains the spreading of waves but also the transformation of physical properties like charge. By applying principles from classical physics and modern quantum theory, we gain a deeper appreciation for the interconnectedness of waves, particles, and the universe itself. As our understanding of diffraction and wave-particle interactions grows, so too does our ability to harness these phenomena for new technologies and deeper scientific insights. Whether in exploring the origins of the universe or developing advanced communication systems, the study of diffraction remains at the frontier of discovery.